Hello everyone. So today our topic is about waves and sound. Okay, and for this slide we have three parts. The first part is about transverse and shooting waves. Second part is about wave effects, and the third part is about sound waves. Okay, so let's move into the first part about transverse wave of the shooting waves. Okay, so here you can find in these slides. Here is a hand are moving a spring, right? And you can find the hand is moving like this direction, right? It's moving just upwards and downwards. But for the spring, you can find it vibrates from the left to the right, right? It's just like a sine function as this way, right? Okay. So you can find here, if you want to describe the property for this wave, you can say that here, there is a source, like the source of the hand, right? The source vibrating direction is like perpendicular to the wave traveling direction, right? So we can say that the transverse is just like this way, okay? So here, if you set the property first is the source vibrating direction just equals to the wave traveling direction. Okay. Oh, sorry, perpendicular. Sorry. Okay. Here is perpendicular to wave traveling like direction. Okay. This is the first property of this. Okay. So maybe you can just list some very like connected examples. Like if you're throwing a stone in the pond, and you can find the pond can just have loops of the ripples, right? Like this way. Okay. And you can find the ripples just traveling from the center of the stone to the edge, right? And we can find the red arrow is represented for the wave traveling direction, right? But for the stone hitting on the pond, you can find the wave just vibrate like this way, okay? So you can say that you can find the wave or source operating direction just perpendicular to the wave traveling direction. So you can say that there is a transverse wave, okay? So this is very important in your daily life, okay? So we can say that maybe for the like sound, or like here the stone hitting on the pond, they are both transverse wave, okay? This is because here. And another property is that if you're just seeing through the spring, just imagine it is combined with several particles like this way. Like here are different purple particles connected together in this direction, and you can say that why the spring can travel like this way. That is because at the very first beginning, the hand starting to vibrate, and it gives the first particle or first spring particles moving direction, just upward and downward, right? And because of it is solid, so most of the particles just connected together and they can take the second particles to vibrate, okay? And the second particles vibrating, and they can let the third particles vibrate, okay? So it can transfer the energy through the vibrating because they are very combined together closely, okay? This is for this reason. So we can say that if you see a particle perspective, and this is because vibrating, okay? Because vibrating can transfer energy, okay? This is for the transverse wave, okay? So please remember for this and try to like maybe this like describing the transverse waves like this way, okay? Just using the particles view, okay? So after that, maybe let's have another example. Like if you're throwing a stone in a pond, you can find the pond is just moving up, the stone just moving upwards and downwards, right? And you can find the wave just traveling from the left to the right, okay? And if you just view the wave at a side view like this, here's the side view, okay? And you can find here the wave just like a sine function, it moves upwards and downwards like this way, okay? And for the pound, if we are moving from like bird view like this way, and you can find here circles of the like ripples, right? And we let the highest point right here as the wavefront, and this is also a wavefront, and there is also the wavefront. We call this the wavefront, and they represent for a highest point in the sine function. Okay. And maybe you have a question. So what about this point? This is a minimum point, right? And maybe here there are also a kind of wavefront like this way. But we only using the highest point to making our wavefronts, okay? So in the graph, you can see that here, from this wave to the another wavefronts, that represent for this highest point to another highest point. So this can also be a period for waves, okay? So this is for the transverse wave to perspective to just understanding for them, okay? So here you can find maybe in our IGCSE test, there are some questions to combine with side views and combine with the bird views. Okay, you can just to try to distinguish about it. Okay, and another way is called longitudinal waves. So what is about longitudinal waves? You can find here your hand just moving from the left to the right, right? And the spring also moving from the left to the right. Okay, and maybe you can find some places is very tense and some places maybe I think it's very like not very tense, right? And why is this? You can find here, because as your hand just moving, your hand is just holding this part, right? Holding part is very tense, but you can find because spring has like a elastic energy, so it can just has a refraction like this way, okay? So we called the very tense places called the compression, okay? Just from the word compress, right? And these places means it's a very further refraction, okay? That means here the particles inside of the places, like they have less energy and they're a little bit far from each other, okay? So if a problem like a P2 or sorry P4 problem asking you what is the difference of compression and refraction, you can tell them that in the compression of the spring, the particles very closely to each other, and in refraction they are very far apart from each other. Okay, but they are the two differences. And here you can find right here the longitudinal waves have the same traveling direction with the source vibrating, right? So we can say that the purport is the source vibrating direction equals to the spring or the wave in the spring traveling direction, right? So here is for the first property for longitudinal waves, okay? And maybe you can using some examples for longitudinal waves like the light or like different kinds of rays. They are all the longitudinal waves, okay? We can just say that electromagnetic waves, they are all longitudinal waves. Okay, here's the property like this. Okay, so maybe you have a question. So how we can use in the compression and the refraction to find the property for the waves? If you have a problem and it gives you this figure, you can just imagine here. You can find the middle of the refraction and find the middle of the find the middle of the compression and find the middle of the refraction, right? And you can find this is about the half the wave or the period of the wave, right? And if you are just choosing two refraction and two compressions to find their middle place, and you can use a line to connect together, that means a period for a waves, right? Or a period in the sine function, right? So therefore, refraction just the same as the compression, they have the same meaning, and you can using this method to find the wavelength, or like you can finding the period, okay? And now we have to describing about the wave equation, okay? And before this, we have to know several understanding of the waves, okay? So we have to first understanding for the word wavelength. So wavelength just like you're doing some math problems, okay? And where you are using IGCSE mathematics, you can find here the period of a sine function is like from a central point to the next central point, right? And this is because it's just moving through a period, and you can find the same shape in the next period, right? So we can say that the red part is a period. And in IGCSE Physics, we just consider about the period as wavelength. So we can say that here the length is 2 meters. So wavelength just means a period of wavelength, okay? So this is for wavelength, okay? And for a second part, you can say besides the wavelength, you have to determine a new property called the like frequency. Okay, so maybe frequency in our daily life means like you have the if you are playing the music, right? You can find the beats in the music, right? So maybe you can set the beats here is frequency. I'll also give you another example where when you are going to Hong Kong, you can find there are traffic lights in Hong Kong everywhere, okay? And they're just like British, okay? And the sound in the traffic light, when the light is just turning red to the green, you can find the traffic light is not very hurry. So maybe you'll find the beep, beep, and beep, like this way, okay? And if the traffic light just want to turn into red, maybe it will have a big, 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 like this way, okay? It will be very hurry and to rush you to go through the road, okay? So you can find here for the for the green light, you can find here the big maybe have a very far time distance, right? Or the time taken is very long, and you can find their last frequency, right? Because only in the period only 3 beep has appeared, right? And if you can find if the light is almost turning to red, you can find the big or maybe the time taken between each beep is very small, but the total time for the beep is very large, right? Like this way. So we can say that once the time taken or time period increases and the number of the beep, or you can say that the frequency of the beep, right, decreases, okay? And once you can find here the time taken decreases and the frequency of the beep increases, okay? So like the time taken and frequency, they are inversed, okay? Like this way, okay? So in IGCSE Physics, we just regarded the frequency as 1 over time taken like this way, okay? This is for the frequency. And you can just trace back to the motion part we had there before, that for motion, we have the constant speed equals to the distance over time taken, right? Like this way. And for distance in wave, we can just regard it as the wavelength, okay? Because wavelength and distance are both represented for the distance, okay? So that's equals to each other. And for time taken in the wave, we can using 1 over f to represent it for it, because the frequency just equals to 1 over time taken, right? So here you can set that the formula finally becomes to the wavelength we can use in lambda to represent for this, and the frequency we can use in f to represent for this. So this is our wave equation. Velocity of the wave equals to the wavelength times frequency, okay? And remind here that there are different units for different proportion. Here the velocity unit is meter per second, right? And for frequency, the unit is hertz, or you can say that is 1 over second. And for lambda wavelength, the unit is meter, okay? So here are the 3 different symbols in here, okay? And it's here about unit, okay? And here's a little bit example like here. You can find there are a 6-meter wave right here, and you can find after 1 second later, the point just traveled to the last point, okay? So maybe here the question is, how do you distinguish about here the velocity of the wave, okay? This is a problem. So right here, we can use the formula that frequency times wavelength, right? So for the wavelength lambda, we can find it just represented for 1 period of wavelength, right? Like this way. So we can say that here, wavelength equals to 2 meter, because there are 3 wavelengths equals to 6 meter, right? So for 1 wavelength, just equals to 2 meter. And for frequency, we can set here that the total time taken is 1 second, right? And for just 1 period of wave, that is 1 over 3 seconds, right? So here is 1 over 3 seconds. But remember that frequency equals to 1 over time taken, right? So here is 1 over 3 seconds, okay? So frequency here is 3 hertz, okay? So for frequency, we have 3 hertz, and for wavelength, we have 2 meter, and times them together is 6 meter per second, okay? So final wavelength is 6 meter per second, okay? So here is a very clear example for this, okay? And maybe here are some characteristics for the sound waves, like you're in your daily life, we are using knowledge to represent for a sound, right? And in the IGCSE Physics, sometimes we're using amplitude to represent for the lawless, okay? So maybe here you can find here on the waves on the screen, here is a wave has a very big amplitude, right? And like you're using a detector to detect the sound, and here the sound maybe have maybe 50 dB, okay? And here you can find in the next screen, maybe the amplitude here is very small, like here. And now let's maybe here is 330 dB, okay? So maybe you can use in the sound of waves, you can find here's a relationship between each other. So if you said that the amplitude increases, that means the sound or in the daily life or in the real life, the knowledge for sound also increases, okay? So they're maybe they have a similar meaning that one increases, another must be increased, okay? So here is for amplitude and knowledge, okay? And another example is like if you are playing the piano, I remember when I was a child, I played the piano, and you can find from the left to the right, the different key has different sound, right? Maybe at the right of the key, I remember that maybe it has a very highest like very sharp sound, right? And maybe you will find from the right to the left, the sound becomes very dull, right? The two difference between the sound, okay? So here you can find we are using a word in daily life we call pitch, right? Maybe if you're going to like a musical like a musician competition like here, and you can find that you have to first find the pitch before the competition, right? And to adjust all the frequency for the like different keys, right? If you have different frequency or different sound for the keys, maybe your like your music will be different from the original music, right? So you have to check for your instrument, right? And if we use frequency in the IGCSE physics, mostly in some problems to describing the waves, okay? But they have the same meaning and frequency and the pitch, okay? Please remember for this. And here you can find there is a very small edges here. That is the human beings' ear can only hear the sound of 20 hertz to 20,000 hertz. So we can say that we have a limitation. Like for example, maybe if the earthquake comes and maybe our human beings cannot feeling about Earth because we cannot hear any sound, cannot have any feeling. Maybe only if the earthquake comes, we can feeling that the Earth is shaking, right? But for most of the time, we cannot hear it. But for some animals, like animals, like some elephants, like some tigers, or like some insects, okay, and if the earthquake comes, maybe they will feel very like worried and they will hurry up to a very safe shuttle, okay. So maybe there's the difference. So we can only heard about 20 to 20,000 hertz. We cannot heard about the earthquake waves, okay. So there's a difference. Okay, and here is an example. You can just try to solve this problem, please. Okay, I think you have your answer, right? I'm guessing you're choosing A, right? So for amplitude, you can find in the A and B, the wave has amplitude equals to 2, right? So this is for A and B. And for frequency, we can set if the time period is very small, that means it has a highest frequency, right? Because frequency just equals to 1 over time taken, right? So here we can find in A, the time period for the sound is very small, right? And for B, you can find the time taken for one period is very big. So A's frequency is bigger than B, right? So we are choosing the A, right? Okay, so this is for today's our lesson and see you next time. Bye.